Tonight, we're going to explore one of the most quietly unsettling truths about our own solar system. We picture the planets as neighbors, 8 worlds sharing the same small patch of space. But Neptune sits so far out that the gap between it and Mercury dwarfs the entire distance from Earth to Mars by a factor of nearly 60. We have only ever seen it up close once. When Voyager 2 swept past in 1989, it found a world 17 times the mass of Earth, with winds screaming at 1,200 miles an hour, radiating more than twice the heat it receives from a sun that hangs in its sky as little more than a bright star. But here is the part that should stop you. Neptune is not the edge of the solar system. It is the edge of human belonging, a line drawn inside our own star's domain, beyond which Earth quietly stops working as home, and the body, the mind, and every machine built to keep us alive begin to fail. By the end of tonight, you're going to understand why a crude journey to Neptune would not be exploration in any sense we would recognize, how every system that sustains human life breaks down at that distance, and what it would truly mean to cross from exploration into something closer to voluntary exile. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The edge of human belonging. That phrase deserves a moment, because most of us carry an image of what that boundary looks like, and almost everything about that image is wrong. Think about the diagram. You have seen it hundreds of times. 8 planets lined up in a row, Mercury close to the Sun, Neptune at the far end, and everything in between arranged with roughly equal spacing, as if the solar system were a well-organized neighborhood where every planet had a reasonable address on the same street. Textbooks carry it, classroom posters carry it, documentaries open with it, and because we have seen it so many times, we have absorbed it as something close to physical fact. It is not a simplification, it is a fundamental distortion. The distance from Earth to Mars, the gap that looks in the diagram like a short step down the street, represents roughly 140 million miles at a typical close approach. The distance from Uranus to Neptune, which in the diagram looks like roughly the same step, is more than 1.6 billion miles. And the full span from Mercury to Neptune is compressed so severely that the ratio between the smallest gap and the largest comes out to nearly 60 to 1. The diagram takes that 60 to 1 difference and flattens it into equal visual spacing. What looks like a garden you could walk across in an afternoon is a desert you cannot cross in a lifetime. This matters because the distortion is not just visual, it rewires intuition. If you have grown up with that diagram, you have spent your entire life believing, on some deep level, that Neptune is the next stop on a continuum, that you could visit Jupiter, swing past Saturn, and cruise onto Neptune with a bit more fuel and a bit more patience. The logic feels sound. The planets are all there on the same street. But here's where it gets strange. Neptune does not sit at the far end of a neighborhood. It sits at the edge of a different category of distance entirely. A distance so vast that reaching it breaks the vocabulary we use to describe spaceflight. Words like exploration, communication, rescue, return, home. Those words carry assumptions built from closer destinations. They work for the Moon. They work for Mars. They work mostly for Jupiter. At Neptune, they stop working in the ways we expect. We will get to exactly why. But first, consider what waits at that address. Neptune is the 8th and outermost major planet. It belongs to a category called ice giants, a classification it shares only with Uranus. Gas giants like Jupiter and Saturn are built mostly from hydrogen and helium, the 2 lightest elements. Enormous and relatively straightforward in composition. Neptune and Uranus are different. Their interiors hold substantial quantities of heavier volatile compounds, water, ammonia, methane, not in liquid or gaseous form as we know them on Earth, but compressed by enormous internal pressure into exotic states that behave like neither solid nor liquid. Dense, hot, strange. The planet itself is not small. Neptune's equatorial diameter is roughly 31,000 miles. nearly 4 times the width of Earth. Its mass is about 17 times Earth's. And if you hollowed Neptune out completely, you could fit approximately 60 Earths inside it. It is not a minor world tucked at the outskirts. It is a giant, but its size is not the strange part. The strange part is what happens in its atmosphere. Neptune receives only a tiny fraction of the sunlight that reaches Earth. The sun, from Neptune's distance, is just a very bright star. By every reasonable expectation, Neptune should be quiet, cold, still, a frozen world dimly lit and slowly drifting. It is not. Neptune hosts the fastest winds ever measured on any planet in the solar system. Sustained speeds reach up to 1,200 miles per hour. Gusts push toward 1,500 miles per hour. A Category 5 hurricane on Earth, one of the most violent storms our planet produces, peaks at around 157 miles per hour. Neptune's winds blow at roughly 10 times that, and they blow westward, opposite the direction of the planet's rotation, which is itself strange. Something is driving this. Something from inside. Neptune radiates about 2.6 times more heat than it receives from the sun, which means there is an internal heat source pumping energy outward through the planet. What mechanism generates that heat? We do not know. The full energy budget driving those violent winds remains one of the genuinely open questions about this world. Then, on August 25th, 1989, everything changed. That was the date Voyager 2 made its closest approach to Neptune, the only spacecraft to ever visit the planet, completing a journey of 12 years after leaving Earth. What Voyager found rewrote the picture. In Neptune's southern hemisphere, a vast storm churned in the atmosphere. Scientists named it the Great Dark Spot. It was anticyclonic, rotating counterclockwise, and it was roughly the size of Earth, a vortex the diameter of our entire planet, spinning in the atmosphere of a world we had barely begun to understand. 5 years later, the Hubble Space Telescope looked again. The Great Dark Spot was gone. Not diminished, not faded, gone entirely. A storm the size of Earth had dissolved in 5 years, as if the planet's atmosphere was so dynamic, so energetic, that even planetary-scale weather was temporary. New storms had appeared elsewhere. The atmosphere was not a fixed landscape. It was a living, churning, constantly reshaping system powered by something we still cannot fully explain. None of that is the strangest thing about Neptune. Triton is. Triton is Neptune's largest moon, and from the moment astronomers studied its orbit, something was wrong. Almost every major moon in the solar system orbits in the same direction as its planet rotates. This is a signature of formation. Moons that formed from the same rotating disk of material that built their planet naturally end up moving in the same direction. Triton does not. Triton orbits retrograde. It goes the wrong way around Neptune, moving opposite to the planet's rotation. There is essentially one explanation for that. Triton did not form with Neptune. It was captured. It is almost certainly an object from the Kuiper Belt, the vast reservoir of frozen bodies beyond Neptune that wandered too close and was gravitationally locked into orbit. Neptune took a moon from somewhere else. Triton's surface is colder than any other solid surface in the solar system, a frozen shell of nitrogen and methane ice. By everything we know about geology and internal heat, this moon should be dead. In 1989, Voyager 2 photographed nitrogen gas geysers on Triton's surface, dark material spraying miles upward into its thin atmosphere. Not ancient impact scars, not passive features, active eruptions. Triton is geologically alive, not dormant, not remnant, alive. A captured moon, in a retrograde orbit, colder than any planet, erupting in the dark. And we have barely begun to discuss how far away all of this is. How far away is all of this? The numbers exist. Neptune orbits the Sun at an average distance of about 30 astronomical units. 1 astronomical unit is the average distance between the Earth and the Sun, roughly 93 million miles, or about 150 million kilometers. Multiply that by 30 and you get approximately 2.8 billion miles, about 4.5 billion kilometers. Those figures are real. You can read them, write them down, repeat them. but reading a number is not the same as understanding it. 2.8 billion miles has no emotional weight. It sits on the page the way a very large integer sits on a page. Correct. Inert. Impossible to feel. So the numbers alone will not work here. We need something else. Imagine you're going to build a scale model of the solar system. A physical model. Something you could walk through. You start with the sun, and you represent it with a standard basketball. A basketball is about 9.5 inches across. To make that substitution work, you have to shrink everything by a factor of roughly 9.2 billion. Every distance, every diameter, every moon and ring and gap between worlds, scaled down by that same factor. 9.2 billion to 1. Now you have a basketball sitting on a table. That is your sun. Where is the Earth? At this scale, the Earth shrinks to a bead about 2 millimeters wide, smaller than a peppercorn. You place that bead roughly 86 feet from the basketball, about the length of a generous living room or a short hallway in a school. The basketball is still clearly visible from where the Earth bead sits. You could look back at the sun from Earth and see it without any trouble. That feels right. That feels like the solar system we know. Mars sits at about 130 feet from the basketball, a grain about 1.4 millimeters across. You and the Earth bead and the Mars grain are all in the same parking lot. You could shout across the distance. The sun is still there, still visible, still big enough to register. The inner solar system feels navigable. It feels like a neighborhood. Jupiter is a marble about an inch across, sitting roughly 450 feet from the basketball. A few blocks. You have left the parking lot. You might have walked through a small park and past a row of buildings, but you could still stroll back before your coffee got cold. You can still see the general direction of the basketball if you know where to look. Saturn is a slightly smaller marble, at about 830 feet. A serious walk, but nothing more than that. 15 minutes, maybe 20, and you could move from the basketball sun through Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and back again. The entire span from the sun through the largest planet in the solar system fits inside a space you can cross on foot in an afternoon. That is the inner solar system. A tight cluster, a front yard, a neighborhood where every world is within reach, and the sun anchors the whole picture. The picture did not hold. Uranus is a small bead, sitting about a third of a mile from the basketball. Not a few blocks, a third of a mile. You have left the building, you have left the parking lot. You have walked past several intersections, past other neighborhoods, and you are now standing several blocks away, holding a tiny marble in your palm. If you look back, the basketball is a distant and small object. You can still see it if the street is clear, but it no longer dominates the view. It has become a thing you have to look for. And then, you come to Neptune. Neptune is a bead about 9 millimeters wide, about the size of a small pea, and it sits roughly half a mile from the basketball. Half a mile. To visit Neptune in this model, you leave the basketball, you walk half a mile down the street, and when you arrive, you stand there holding a small pea and you turn around. You look back toward where you started, and you cannot see the basketball. It is half a mile away. Buildings are in the way. Trees are in the way. The street curves or rises or simply carries more distance than your eyes can resolve. The sun is there, somewhere behind all of that, but you cannot see it. You are standing at Neptune's position in the solar system, and the star that this world orbits, the source of light and gravity that defines the entire system, is invisible from where you are standing. Not diminished, not reduced to a small bright point. Invisible. That is what the scale model teaches. Not the distances as digits on a page, but the distances as something your body can process. The solar system is not a row of evenly spaced objects. It is not a neat arrangement where every world sits at a similar remove from its neighbor. It is a dense cluster of worlds near the center, where distances are walkable and the sun fills the sky, and then a vast emptiness, and then a small number of lonely worlds scattered at the edge of the outer darkness. The sun's front yard holds Mercury, Venus, Earth, and Mars. Jupiter and Saturn are the same general block, farther but still within reach. Uranus and Neptune occupy a different part of town entirely, not far in the way that the next town is far, far in the way that a place becomes unreachable in any practical sense. And this matters because Neptune is not simply the 8th planet on a list. Neptune is a world of a completely different category. It sits in a region of the solar system where the sun is a bright star, not a sun, where the distances between here and anywhere else are measured not in steps, but in years. The basketball model makes that concrete in a way that 2.8 billion miles never could. The numbers were always true, but now the numbers mean something. And the distance is only the beginning of what makes Neptune so difficult to reach. Half a mile in the basketball model. That is the crossing. And the question worth sitting with now is not how large that gap is, but how long it takes to cross it. Start with the fastest crewed vehicle ever built. The Apollo command module, returning from the moon, reached roughly 25,000 miles per hour. That is not a slow vehicle, it is the speed of a rifle bullet multiplied many times over. In the basketball model, that speed works out to about 1/4 of an inch per hour, a patient hand moving a marble that slowly would barely seem to be moving at all. At that pace, the journey from the basketball sun to the Neptune P would take more than 10,000 years. 10,000 years is not a long trip. It is the entire span of recorded human civilization. Agriculture, writing, cities, every empire that ever rose and fell, all of it would not be enough time. But the reality was different. The Apollo capsule is our ceiling. That is the best we have ever done with human beings aboard a spacecraft. And it is not nearly enough. Try something slower and more familiar. A car on a highway, driving at 70 miles per hour, no stops. You start the engine. You pull onto the road. You drive. How long to Neptune? About 4,500 years. The Egyptians were laying the first stones of the Great Pyramid at Giza roughly 4,500 years ago. If you had started driving then, you would not have arrived yet. You would still be somewhere in the outer solar system, not yet at your destination, the pyramid long since buried under centuries of sand. A commercial airliner does better. At 550 miles per hour, the same crossing shrinks dramatically. It takes only about 580 years. That sounds encouraging until you reckon with what 580 years actually means. You would have boarded that flight nearly half a century before Christopher Columbus reached the Americas in 1492. You would be landing only now. These are not slow vehicles by any reasonable human standard. A 70 mile per hour car is the ordinary pace of an ordinary afternoon on an ordinary road. A 550 mile per hour airliner is how we cross continents. The fact that these machines require civilization-spanning durations to reach Neptune is not a quirk of the comparison. It is a precise description of what the distance means. Now consider light. Light travels at 186,000 miles per second. Nothing in the universe moves faster. Light leaving the sun reaches Earth in about 8 minutes. It reaches Mars in roughly 12.5 minutes. Jupiter is 43 minutes away at light speed. Saturn is 79 minutes, a little over an hour and a quarter. And Neptune? 4 hours and 10 minutes. Not 8 minutes. Not 43. 4 hours and 10 minutes. More than half a standard workday. And that is for a photon moving at the universe's absolute speed limit. The sun rises, you begin your morning, you get through several hours of your day, and only then does the light that left the sun as you woke arrive at Neptune. That gap between Saturn at 79 minutes and Neptune at 4 hours and 10 minutes is not a small step. It is a wall. A photon that crossed from the sun to Saturn in the time it takes to watch a long film still needs nearly 3 more hours to finish the journey to Neptune. And this is not merely an interesting comparison. It is a structural fact about every mission ever attempted or imagined at Neptune's distance. Because light travel time is communication time, a radio signal, an emergency transmission, a course correction from mission control, a response to a question from the crew, all of it travels at the speed of light. All of it takes 4 hours and 10 minutes one way. That is the flaw. That is not the result of bad equipment or limited bandwidth. It is physics. A crew at Neptune sends a message. They wait. 8 hours and 20 minutes pass before they hear back. Any emergency that requires a real-time human response from Earth is, by definition, an emergency the crew must resolve entirely on their own. That single fact reshapes what a crewed mission to Neptune means, and the implications are larger than they appear right now. But first, there is the question of where Neptune actually sits in the solar system. Because the light travel times suggest a gradient, a steady outward progression, planet after planet, each a little farther than the last, and that picture is wrong. The inner planets, Mercury, Venus, Earth, Mars, cluster within roughly 1.5 astronomical units of each other. Mars, the farthest serious target any crewed mission has ever aimed for, sits at about 1.5 astronomical units from the Sun. The entire inner solar system, every world humans have set foot on or sent serious spacecraft to in the crewed sense, fits inside a sphere with a radius that corresponds to Mars's orbit. Then the asteroid belt. Then Jupiter at 5.2 astronomical units. Already more than triple the Earth to Mars distance. Saturn at about 9.5 astronomical units. Uranus at roughly 19 astronomical units. And then something unexpected happens. Between Uranus and Neptune, there is a gap of approximately 11 astronomical units. 11 astronomical units of essentially empty space before the next planet appears. That number needs to land clearly. The distance from the Sun to Saturn, the distance that spans the entire inner solar system, and the first two gas giants, is about 9.5 astronomical units. The single gap between Uranus and Neptune is larger than that. Not comparable to it. Larger. You could fit the entire span from the Sun to Saturn inside the Uranus to Neptune gap, and still have room left over. Neptune does not sit at the far end of a continuum. It sits on the other side of a chasm that is wider than everything that comes before Uranus combined. Think about it this way. If you walk the basketball model, you would pass through the inner solar system, through the outer giants, reach Uranus after about a third of a mile, and then begin a second-long crossing before Neptune appears half a mile out. The last leg of that walk, from Uranus to Neptune, covers more ground than the entire walk from the basketball sun to Saturn. The outer solar system is not the far end of a street. It is another country entirely, and this matters beyond architecture. Every challenge a spacecraft faces scales with time and distance. Fuel burns for longer. Food and water and oxygen must last longer. Radiation accumulates for longer, because spacecraft and crews spend more years in deep space, exposed to cosmic rays and solar particle events with no atmosphere and no magnetosphere to offer protection. Equipment that is designed to last years must last decades. Communication delays that are merely inconvenient at Mars become operationally dangerous at Neptune. And human beings, isolated in a small vessel, cut off from Earth in any meaningful real-time sense, face psychological pressures that no mission in history has ever had to plan for at this scale. The chasm is not a metaphor. It is a precise description of what separates Neptune from every other serious destination in the solar system. Physics, engineering, biology, and psychology all converge at the same moment, all scaled to their most extreme values at once. And that convergence is where this story is really headed. Only one traveler from Earth has ever made that crossing. It was not crewed. It could not have been. And the story of how it reached Neptune at all is a story about what it costs even a machine to get there. Voyager 2 launched from Cape Canaveral on August 20th, 1977. It was not aimed directly at Neptune. A direct flight using conventional chemical propulsion would have taken roughly 30 years. 30 years to arrive at a single destination, with no gravity to brake against, no refueling, no margin. Engineers could not accept that. So instead, they waited. They waited for a rare alignment of the outer planets, a configuration that allowed the spacecraft to swing past Jupiter, then Saturn, then Uranus, borrowing speed from each planet's gravity field without burning additional fuel. A cosmic billiard shot, each planet a cushion redirecting the cue ball farther out into the dark. That alignment will not repeat until the 22nd century. Even with those assists, the journey took 12 years. 12 years from launch to arrival. 12 years of the spacecraft traveling through the outer solar system, silent and alone, with no crew, No corrections from anything except the occasional uplinked command from Earth. And then, on August 25th, 1989, Voyager 2 reached Neptune. The flyby itself lasted hours. 12 years of travel for a window measured in hours. That ratio is worth sitting with. The spacecraft flew past Neptune's North Pole at a distance of roughly 3,000 miles, moving at approximately 19 kilometers per second, about 42,000 miles per hour. In that narrow window, it captured the first close-range images of Neptune and its moons ever taken. The only close-range images ever taken. The answer was stranger than expected. Neptune receives so little sunlight that the cameras needed long exposures to gather enough light to form a clear image. Long exposures on a spacecraft hurtling past at tens of thousands of miles per hour would normally smear every image into a streak. Engineers could not slow the spacecraft. They could not give it more time, so they programmed it to rotate during each exposure, tracking the planet below, turning at precisely the rate needed to keep Neptune steady in the frame, panning a camera to follow a moving subject. Performed autonomously, with no operator, 2.8 billion miles from Earth, with a round-trip communication delay that made real-time correction impossible. Not approximately, not close, perfectly. The images came back sharp, cloud bands, storm systems, the dark arc of a partial ring, a moon they had barely seen before, now resolved into a world. Voyager 2 had solved, in real time and in deep isolation, a problem that would have defeated any simpler machine. And it is worth being precise about what kind of machine it was. Voyager 2 weighs approximately 825 kilograms, less than a small car. It carries no food, no water, no breathable air. It does not sleep. It does not age in any medical sense. It does not accumulate radiation damage in tissue because it has no tissue. It experiences no fear of the dark, no longing for home, no despair at the distance still ahead. The engineering required to send it across 2.8 billion miles was immense. But the engineering required to send human beings across that same distance is of a categorically different order. A crewed spacecraft must carry all of those things Voyager did not need. And it must not only reach Neptune, it must slow down enough to orbit, to operate, to survive, and eventually to begin the journey back. Voyager never slowed. It could not have. That was the only reason the mission was possible at all. Now think about what the spacecraft found when it arrived. Not just the storms and the moons. Something more fundamental. Neptune exists at a level of faintness that human senses were never designed for. At Neptune, noon resembles the last grey minutes before nightfall on Earth. Permanent, still, pale. Not dimmed sunlight, not a weaker version of a sunny afternoon. A different quality of light entirely. The kind of light that tells the eye the day is ending and will not restart. That has always been Neptune's nature. It has always exceeded what human senses can reach. The ancient Greeks identified 5 wandering stars: Mercury, Venus, Mars, Jupiter, Saturn. These were the planets. They moved against the fixed background of stars, and that motion was enough to find them. No one knew 2 more planets existed beyond Saturn. The sky did not reveal them. Uranus was found in 1781, and even then, only barely. William Herschel spotted it through a telescope, and initially mistook it for a comet, a planet misidentified as a small, icy interloper, because it barely looked like anything at all at that distance. Neptune was never found by looking, it was found by calculating. In the 1840s, astronomers had accumulated years of careful observations, showing that Uranus did not move the way Newton's laws predicted it should. Something was pulling on it, something unseen, somewhere farther out. The French mathematician Urbain Le Verrier analyzed the deviations and worked backward. He calculated not just that an unseen planet existed, but where it was, and approximately how massive it had to be. Then he sent that prediction to the Berlin Observatory. On September 23rd, 1846, astronomer Johann Galle pointed a telescope at Le Verrier's coordinates. Neptune was there, within 1 degree of the predicted position. Not discovered by a bigger telescope, not found by a stroke of luck or years of patient sky surveys. Discovered by mathematics, confirmed by a single night of observation. A planet located first in the mind, then in the sky. It was the first planet ever found that way. Fitting. Because Neptune has always been defined by its resistance to direct perception. You cannot see it with unaided eyes. You cannot feel its gravitational pull from where you stand on Earth. The Sun, viewed from Neptune's distance, is reduced to a sharp, brilliant point of light, roughly 900 times dimmer than a sunny afternoon on Earth. Not a disk, not the warm, expansive presence that fills the summer sky. A point, brilliant but cold, no longer a source of warmth, no longer something that commands the entire field of view. And somewhere near that point, lost in its glare, would be Earth. This is the world Voyager 2 visited. This is the world that yielded its secrets only to mathematics and to patient machines. And the reason that matters is what it implies for everything that comes after. Every fact Voyager returned, every image it captured, every surprise it found in those brief hours of proximity came from a machine that never had to sustain a life. The moment that changes, the moment you add a human being to the equation, the problem does not get harder in degree. It gets harder in kind. What that actually means in practice is where the story turns next. Light takes 4 hours to cross that gap, and so does every word home. Think about what that means for a moment. Every crude spaceflight in history has depended on something more fundamental than oxygen, more foundational than water. It has depended on the ability to hear a voice and receive an answer. On the International Space Station, astronauts are never truly alone. Mission control in Houston stays in continuous contact. Moscow stays in contact. The delay between a question asked and an answer received is negligible, indistinguishable from a phone call between cities. That connection carries equipment troubleshooting, medical consultation, psychological counseling, family video calls. Engineers on the ground can pull up schematics in real time, talk a crew member through a repair, escalate a medical situation to a specialist within minutes. The support web around any active mission is vast, deeply staffed, and always live. That web is not a convenience. It is the reason human spaceflight works. Now consider what happens when you begin pulling that web apart. NASA's Human Exploration Research Analog Program, known as HERA, operates out of Johnson Space Center. It simulates the isolation of deep space missions by placing small crews in confined habitats and introducing controlled communication delays. Researchers have studied what even modest delays do to crew performance and psychological health. What they found should not be reassuring. Studies on the International Space Station imposing a one-way communication delay of just 50 seconds showed measurable degradation. Not catastrophic failure, measurable degradation in crew well-being, communication quality, task efficiency, and rapport with mission support. Less than a minute of delay, and the cracks begin. At 5 minutes of one-way delay, real-time problem-solving becomes functionally impossible. The exchange has already broken. You are no longer having a conversation. You are leaving messages. Mars already sits at the edge of that boundary. At its closest approach, Mars is roughly 3 light minutes from Earth, making the round-trip communication time around 6 minutes. At its farthest, the one-way delay stretches to 22 minutes, and the round trip to 44. NASA considers this a serious, partially unsolved challenge. Engineers are already developing AI countermeasures, automated psychotherapy tools, and enhanced crew training protocols to compensate for the loss of real-time ground support. At Mars' maximum distance, the support web is not intact. It is degraded to the point of requiring fundamental redesign. Neptune is not slightly farther than Mars. The one-way delay is approximately 4 hours. The round trip is roughly 8 hours, a full working day. Here is what that means in practice. Apollo astronauts communicating with mission control during the lunar missions experienced a one-way delay of about 1.3 seconds. Round trip, about 2.5 seconds. At Neptune, the one-way delay is roughly 11,000 times longer than what the Apollo crews experienced. Not a slower version of the same conversation. A different thing entirely. Think about a pressure seal crack. An air leak. Gradual, but worsening. On the International Space Station, this is a coordinated emergency. Flight directors are notified immediately. Structural engineers pull up the relevant diagrams. A response is being assembled in real time while the crew is still assessing the situation. The first instructions arrive within minutes of the first report. The problem exists inside a web of collective intelligence, all of it operating simultaneously, all of it live. At Neptune, the crew transmits the report. Then 4 hours pass. Mission Control receives the message. Engineers gather. A response is assembled. 4 more hours pass while that response crosses the void. By the time the first word of guidance arrives, 8 hours have elapsed. The crew has either solved the problem or they have not. The instructions from Earth arrive as history, not help. They describe what might have worked, addressed to a situation that no longer exists. But here is where it gets strange. The communication delay is not simply a slowness problem. It does not just mean that help arrives late. It means that the temporal structure of conversation collapses entirely. A conversation requires two minds reacting to the same moment. A question, an answer, an adjustment, another question. Strip that away and what remains is not a slow conversation. It is two people leaving recorded messages for each other, each responding to a version of the other that is already 4 hours out of date. Every exchange becomes a pair of mismatched monologues, separated by a day's worth of silence. Medical emergencies make this concrete in the starkest possible terms. A cardiac event on the International Space Station brings an immediate real-time consultation with a flight surgeon. If the situation warrants evacuation, a Soyuz or Crew Dragon vehicle is available. The nearest hospital is hours away at most. At Neptune, there is no evacuation. There is no flight surgeon answering in real time. There is no hospital within a decade of travel. An appendicitis, a stroke, a broken femur. Any of these must be treated by crewmates who are scientists and pilots. They are not surgeons. They would carry medical training. They would carry manuals and preloaded resources. But they would face those decisions without a specialist on the line, in the middle of a 4-hour silence, relying only on what they brought with them and what they already know. The psychological dimension follows the same logic. Private psychological conferences between crew and ground support, already a standard element of long-duration spaceflight, become exchanges of recorded messages. A crew member describes what they are experiencing. 4 hours later, a therapist responds to that description. 4 more hours pass before the crew member hears the response. The therapist is reacting to a state of mind that is now 8 hours old, reconstructed from a recording, unable to ask a clarifying question, and receive the answer in the same session. Family video calls undergo the same transformation. A parent speaks to a child. Hours pass. By the time the reply arrives, the child has gone to bed. HERA campaigns of 45 days, with relatively minor communication delays, already showed perceived social support declining over time among crews. Extrapolated to missions measured in years, with 4-hour delays in every direction. The picture is, by NASA's own assessment, deeply alarming. NASA has explicitly acknowledged that deep space missions will require unprecedented levels of crew autonomy in psychological self-management. AI companions, automated psychotherapy, preloaded mental health resources, all of these are under active investigation. Whether any of them can functionally replace real-time human connection across a void that large is not yet known. And then there is the link itself. When Voyager 2 reached Neptune in 1989, its signal had traveled 2.8 billion miles to reach Earth. It arrived so faint that the Deep Space Network, the global array of large radio antennas that maintains contact with deep space probes, had to expand its primary receiving dishes from 64 meters to 70 meters in diameter, and link multiple antennas together just to collect enough signal to read the data. The data rate dropped to a fraction of what a modern device streams without effort. That was sufficient for a small robotic probe, transmitting instrument readings and images. A crewed mission would require orders of magnitude more. Voice communication, video, continuous telemetry from the spacecraft systems, medical monitoring data, all of it flowing in both directions, continuously, for years. The infrastructure sustaining that link would need to operate without interruption across a decade. Any disruption, a solar conjunction when the sun's radio noise drowns out the signal, an antenna failure, a pointing error too small to notice until the contact window closes, and the link does not degrade. It severs, not a weaker signal. Silence. Hours of it, possibly days, with no way to know from inside the spacecraft when it will return, or whether it will return at all. That silence is not an inconvenience. It is the deepest form of isolation human beings would ever have experienced. Cut off from Earth, unreachable and unable to reach, the crew would exist in a state that no amount of training fully prepares a person for. The communication link stretching back toward the sun is, in every meaningful sense, a tether 4 light hours long and fragile as a whisper. And communication is only one of the systems that begins to fail at this distance. And if they cannot speak to Earth in real time, can they at least still see it? The answer is no. Not difficult to make out. Not reduced to a faint smudge. Gone from the visible sky entirely. This is a consequence of a simple law. The inverse square law governs how light spreads across distance. Double the distance from a light source and you receive not half the light, but a quarter. Triple the distance and you receive a ninth. The relationship is ruthless and exact. Neptune sits roughly 30 times farther from the sun than Earth does. Run that through the inverse square law, and the result is that Neptune receives barely 1/10 of 1% of the illumination Earth receives. Not a dimmer version of daylight, a different category of light. Standing on Neptune at noon, you would not see a bright day softened by clouds. You would see something closer to the last grey moments before nightfall on Earth. That particular quality of light, pale and attenuated, the kind that tells the eye the day is ending and will not restart. That is high noon at Neptune. The sun is still there. It is still the brightest object in Neptune's sky by a wide margin, but it is no longer a warm presence. It is no longer something that fills the field of view. It hangs above you as a brilliant, sharp point of light, still recognizably the sun, no longer a sun. And then there is Earth. At its closest approach, when the two planets are on the same side of the sun, Earth and Neptune are separated by roughly 29 astronomical units. At that distance, Earth falls well below the threshold the human eye can detect. Not a blue dot visible against the dark. Not a faint pixel you could point to unaided. Nothing. A crew standing at a window, scanning the sky, would find no trace of it. The home planet is simply not there. A telescope changes that. Through an eyepiece, Earth would appear as a pale blue pixel, a single point of color adrift near the sun's position in the sky. It is there, detectable, measurable, real, but step away from the eyepiece and look out the window and there is nothing. No visual confirmation of home. No blue light to locate yourself against. The universe through that window looks almost exactly like the universe from Earth. Same constellations, same patterns. Neptune's position in its orbit shifts the background stars so slightly that the shapes of the constellations are essentially unchanged. The sky looks familiar, except for the one object that would have made it feel that way. That one object is gone. This matters in ways that are easy to underestimate. Every human explorer in history has had some form of visual access to home. Sailors on the Pacific spent months out of sight of land, but looked up at the same sun, the same moon, the same stars that rose over the harbors they left behind. Researchers overwintering at Antarctic stations endure months of isolation, but the moon crosses their sky. Apollo astronauts, on their way to the lunar surface, looked back and saw Earth as an enormous, luminous sphere, continents visible, oceans blue, the Terminator line sweeping slowly across the face of the planet. They could see where they'd come from. They could point to it. Some of them described being able to identify the rough geographic region where their families lived. That image, Earth suspended in darkness, fills some of the most iconic photographs in human history, precisely because it carries something no other image carries. It is home, visible, real, still there, still beautiful. That image does not exist at Neptune. Researchers at NASA have studied what the loss of that view costs a crew. The findings are consistent. Astronauts aboard the International Space Station describe Earth observation as one of their most important psychological resources. Many name photographing Earth through the cupola as their most valued recreational activity. Looking down at home, watching coastlines drift past, watching storm systems spiral across ocean surfaces, watching city lights emerge on the night side is not merely pleasant, it is restorative in a measurable way. NASA researchers designate it as a psychological countermeasure, a deliberate tool for maintaining well-being during long missions. The phenomenon even has a name, the overview effect, the cognitive and emotional shift that comes from seeing Earth as a whole, fragile, borderless, alone in the dark, a thing to be returned to and protected. Astronauts who have experienced it describe it consistently, across nationalities, across missions, across decades. At Neptune, the overview effect does not exist. There is no Earth to photograph through the window. There is no home visible below. There is a foreign ice giant, blue-grey and remote. There is a captured moon circling backward, venting nitrogen from geysers in its surface. There is a sun that looks like a star. And there is a crew, cut off from real-time communication, unable to hear Earth in anything resembling a conversation, and now unable to see it at all. Think about the layering of that. The communication tether we covered before is 4 light hours long and fragile as a whisper. It carries only recorded messages. It responds to nothing in real time. And now the visual anchor, the thing every human who has ever left home has retained in some form, is gone too. Not weakened, not replaced by something smaller, simply absent. The lighting conditions at Neptune had always been treated, in the literature, as an engineering challenge, a comfort concern, a matter of supplemental lighting in crew quarters. But the loss of Earth from the visible sky is not a comfort issue. It is the removal of something no previous explorer in history has had to go without, a visual horizon to home, a point of light that says, however far you have traveled, the place you came from still exists, still hangs there, still shines. On the lunar surface, Earth fills a significant portion of the sky. Even on the Martian surface, Earth is visible to the naked eye as a bright blue-white star, unmistakable, reachable looking. The visual thread back remains intact. At Neptune, it does not, and the crew would know that. They would know that somewhere inside the glare of the star behind them, their planet is there, invisible, unreachable, 40 times farther than Mars. And there is nothing to look at that would make it feel real. That is one severed connection. And it is not the last one. Even the messages that do arrive carry an Earth that has already moved on. Think about the difference between the ISS and Neptune. On the International Space Station, a crew member can speak to a family member the same way anyone speaks on a phone call between cities. The signal travels the 250 miles home in a fraction of a second. The delay is so small, it is indistinguishable from silence. The conversation happens in shared time. Both people inhabit the same present moment. The astronaut asks a question. The family member answers. The exchange is live. At Neptune, that changes in a way that is not a matter of degree. A message sent from Neptune is already old by the time it reaches Earth. Not slightly delayed. Not a beat behind the conversation. Already a dispatch from the past. 4 hours have passed by the time the words arrive. The person who spoke them has moved on, eaten a meal, slept, woken again. And when the reply travels back, another 4 hours pass. The crew member who asked the question will receive an answer 8 hours after the asking. The whole exchange, a single question and a single response, consumes most of a waking day. But the numbers alone do not capture what this means. The numbers describe a technical inconvenience. What they actually describe is the permanent loss of a shared present. Consider what a shared present actually is. It is the invisible substrate of every human relationship. When two people speak, they assume that the moment one person inhabits is roughly the moment the other inhabits. The same news is news for both of them. The same event is current for both of them. They are, however, separated by physical distance, contemporaries. The present is the thing they hold in common. At Neptune, that is gone. Not weakened, not stretched, gone. Think about what that means concretely. A crew member's child is born on Earth. The parent at Neptune does not know. 4 hours pass before the news arrives. The parent reads the message, sees the image, feels whatever is felt in that moment, and composes a reply. 4 more hours pass before the reply reaches Earth. The child is 8 hours old before a single exchange completes. By the time the parent's first words of love and wonder reach home, the child has already been held, fed, and named in a room the parent cannot see. The parent responded to a birth. The family received a response to a fact that was already history. Or consider the other kind of news. A crew member's parent dies on Earth. The message takes 4 hours to arrive. The tears, the grief, the reaching outward for comfort, all of it travels back toward a planet where the funeral has already concluded. The family has already gathered and dispersed. The condolences from Earth arrive at Neptune in response to a grief they have already processed and begun to absorb. The crew member reaches for connection at the moment of loss and finds only a 4-hour echo of people who have already moved past that moment. These are not hypotheticals designed to illustrate an abstract point. They are the statistical contents of a 12-year journey. A one-way Neptune mission, at minimum, spans 12 years. 12 years is not an abstraction. 12 years is the time in which people are born and grow old enough to have opinions and favorite things and arguments with their parents. 12 years is the time in which parents age and sometimes die, in which marriages stabilize or break apart, in which friends drift or disappear, in which wars begin and sometimes end, in which governments change and technologies transform and the physical shape of cities shifts. The crew would experience all of it. Births, deaths, marriages, divorces, illnesses, recoveries, disasters, elections, discoveries, all arriving on a 4-hour delay, all learned after they had already become history, all responded to after the moment for response had passed. Something else was happening. It is not simply that the crew receives information slowly, it is that the crew and the planet they came from would gradually cease to share a reality at all. Earth as received at Neptune would always be old Earth. Every image, every message, every piece of news would arrive stamped 4 hours in the past. Over months, over years, that accumulates into something more than a delay. It accumulates into a fundamental divergence. Earth would continue to exist and change and evolve in real time. The crew would receive that existence as a series of historical documents, and Earth would receive the crew the same way. The two worlds would drift apart, not only physically, which they already knew going in, but temporally and emotionally and experientially. The crew would know things about Neptune that Earth could not yet know. Earth would know things about itself that the crew had not yet received. They would be, in a real sense, inhabitants of different times. Not distant relatives, not people with different time zones. People marooned in different temporal positions, unable to close the gap, unable to synchronize, unable to share a now. This is the category of loss that has no precedent. No previous explorer has ever been exiled from the present tense of the people they left behind. Sailors on long voyages fell behind on news. Antarctic researchers spent winter months without communication, but they all returned to the same present. The gap closed. The lost time could be caught up. Here, it cannot. The crew at Neptune inhabits a perpetual present that Earth can never touch in the moment it is happening. Every moment the crew lives is already 4 hours old by the time it can be shared. Every moment Earth lives is already 4 hours old by the time the crew can receive it. The two realities run parallel and never intersect. Not a slowdown, a severance. The distance from Earth to Neptune is not only a measure of space, it is a measure of time. It is a measure of the gap between one lived moment and another. And across that gap, nothing is simultaneous. Nothing is current. Nothing is live. Everything that crosses it arrives as a message from the past. A dispatch, not from another place, but from another time. The crew would still be alive, still working, still breathing, still present to each other. But to Earth, they would always be slightly historical. And Earth to them would always be slightly historical. And over 12 years, that slight historical quality would deepen into something the words do not quite reach. They would not only be far from home, They would be marooned in a different present entirely. And the loneliness of that is not the loneliness of distance. It is the loneliness of time. That is the shape of the isolation at Neptune. And it is not the last layer of it. Those years do not only change Earth, they change the bodies crossing toward Neptune. The spacecraft is roughly the size of a modest apartment. Not a generous one, a modest one. The kind with a narrow corridor between rooms and no natural light except through small windows. That is the volume the crew inhabits for the duration of the transit. And the duration is not a year. It is not 2. Under plausible, near-future propulsion, combining chemical rockets with gravity assist from Jupiter, the one-way transit to Neptune runs somewhere between 12 and 20 years. 12 years is the optimistic end. It assumes an optimal launch window, the kind where Jupiter sits in just the right position to swing a spacecraft outward toward Neptune with a borrowed burst of speed. Voyager 2 used that window. Its journey took 12 years. But Voyager 2 did not slow down. It flew past Neptune at tens of thousands of miles per hour and kept going. A crewed mission cannot do that. It must arrive. It must decelerate into orbit. And that changes everything because of a piece of mathematics that does not negotiate. The rocket equation is pitiless. Every kilogram of deceleration fuel a spacecraft carries to Neptune demands additional fuel to accelerate that fuel away from Earth in the first place. That additional fuel demands still more fuel to accelerate it. The mass compounds. The more you need to slow down, the more you have to carry, and the more you carry, the more you have to carry it. Realistic estimates for a crewed Neptune mission stop using 12 as a target. They use 15, 18, 20. A crew launching in their early 30s would arrive in their mid-40s to early 50s. They would have spent their entire middle adulthood inside that apartment. But something was wrong. The problem is not really the time. The time is the container. What fills the container is what matters. And what fills it is biological damage accumulating without pause, year over year, with no comparable precedent in the history of crewed spaceflight. Start with the bones. On the International Space Station, astronauts in microgravity lose roughly 1 to 2% of their bone mineral density per month. The skeleton, deprived of the constant loading that gravity demands of it, simply stops maintaining itself at full density. Countermeasures help. Exercise slows the loss, but they do not stop it entirely. On a 6-month ISS mission, the damage is serious but manageable. Across 15 or 18 years in microgravity, the math becomes dangerous. A skeleton a decade into the transit would be genuinely fragile, brittle in ways that would make suited surface work, physical labor, emergency response a serious medical risk. The muscles follow. Atrophy persists, despite countermeasures, despite the 2 hours of daily exercise that a Neptune crew would have to complete, without exception. 2 hours every single day, not because fitness is a goal, but because the alternative is arriving at Neptune with a body too deconditioned to function in a suit. There is no day off, no recovery week, no option to skip. The exercise is not a health routine, it is structural maintenance. The cardiovascular system deconditions along a similar trajectory. A heart adapted to pumping blood in microgravity for 12 to 20 years would face a serious challenge the moment it encountered any gravity again, even the fractional gravity of Triton's surface. Readaptation would not be a matter of weeks of adjustment. It could be a medical emergency. And then there is the radiation. A 15-year transit accumulates a radiation dose from galactic cosmic rays and solar particle events that is roughly 5 to 7 times what a Mars crew would receive during the transit portions of a 2 to 3 year mission. That figure already pushes beyond the acceptable lifetime limits that space agencies use for Mars planning. A Neptune transit would exceed those limits substantially. The long-term consequences include elevated cancer risk across the crew's remaining lifetime and, based on animal studies and limited human data, the possibility of measurable cognitive decline, memory, processing speed, attention. The brain is not immune to cosmic radiation over years of exposure. We do not know the full scope, but we know it is not zero. And all of that, all the bone loss and muscle loss and cardiovascular deconditioning and radiation accumulation, would still only bring the crew to Neptune. A return trip doubles it. A round trip runs 30 to 40 years. A crew member launching at 32 would return at 65 or 70. Children born just before departure would be in their 30s by the time their parent walked back through a door on Earth. Parents of the crew would almost certainly be dead. Friendships would exist as accumulated video exchanges. Communities would have reorganized entirely around lives that moved forward without them. Think about what that means at the midpoint of the outbound journey. Day 1000 is roughly 3 years into the transit. Neptune is still 9 years away. A crew member wakes in a sleeping compartment about the size of a phone booth, floats out into the common area, and sees the same faces that have been there every morning for the last 1,000 mornings. They know how each crewmate chews. They know what expression appears when one of them is irritated but trying not to show it. They know who hums quietly during maintenance work, and who goes completely silent when something is frightening. There will be no other human face in person for the rest of the decade. Not a visitor, not a stranger at a port, no one. Only these faces in this space every morning until Neptune. The sun is visible through a small viewport, but it is noticeably smaller than it was at launch. 3 years out, the spacecraft sits at roughly the distance between Jupiter and Saturn. The sun is still a recognizable disk, still the brightest object in the sky by a vast margin, but it is smaller than it was, and it will keep shrinking for the rest of the outbound journey. There is no moment when the shrinking stops, no distance at which it stabilizes, and the crew can say, "This is how big the sun looks from here." The contraction continues, relentless and slow, a visual metronome counting down the remaining distance to Neptune. The food is stored provisions and, if the mission carries one, an onboard hydroponic module. Lettuce, radishes, soybeans under artificial light. Research from the International Space Station has shown that growing and eating fresh food provides genuine psychological benefit in long-duration spaceflight. Something beyond nutrition, something about the act of tending a living thing in a sterile environment. Something about color and smell and the texture of a leaf. But the module is also a constant source of anxiety. Fungal contamination spreads faster than expected in enclosed systems. A lighting failure means a crop loss. A water pump malfunction can cascade. The thing that provides comfort is also the thing that can fail, and the crew knows both simultaneously. Daily maintenance fills hours. Filters, sensors, seals. Components designed for 5-year operational lifespans being asked to run for 15. Redundancy has limits. At some point, the spacecraft begins cannibalizing itself, pulling components from non-essential systems to keep essential ones running. The vessel consumes its own structure slowly, year by year, giving pieces of itself to keep the people inside it alive. Birthdays get noted in the mission log, and on day 1000, the mission clock states clearly, without sentiment, that the crew is not yet halfway to Neptune. No historical voyage offers a useful comparison. Magellan's circumnavigation of the Earth took roughly 3 years. Darwin's voyage aboard the Beagle lasted 5. Lewis and Clark completed their expedition across the American continent in just over 2. The most ambitious crewed Mars concepts run 2 to 3 years total. Those missions were grueling. They asked enormous things of the people who undertook them, but the end was always imaginable, always within the range of what the mind could hold as a near future. A Neptune transit has something none of those voyages had: a middle, a period potentially lasting 5 years or more where the crew is too far from Earth to feel any sense of origin and too far from Neptune to feel any sense of destination. Pure transit, no milestone to mark, no landmark to pass, the sun behind them, shrinking, Neptune ahead of them, still years away and barely distinguishable from a star. The crew moves through a region that belongs to neither world, and that region can last longer than Darwin's entire voyage. That is the shape of what duration means here. Not a logistics problem of fuel and supplies, though it is that too. Something else. The crew ages past the years people call their prime. Their bodies adapt away from any planetary surface, any gravity, any sky, and for years at the center of the journey, they occupy a kind of suspension. Not home, not destination. Somewhere in between that has no name and no end date the mind can grasp. The bodies that arrive at Neptune will be different bodies than the ones that left Earth, and what they find there will ask everything those bodies still have left. Surviving that span at all depends on systems that can never be resupplied. Every crewed mission ever flown has depended on a thread running back to Earth. The ISS demonstrates this clearly. The station recycles water, generates oxygen through electrolysis, scrubs carbon dioxide from the air. That loop is genuinely impressive. In 2023, engineers added a new brine processor, pushing water recycling efficiency to roughly 98% of every drop the crew uses. The station generates its own oxygen. It manages waste. From the outside, it looks like a closed system, a habitat that sustains itself. That is when the pattern broke. The ISS receives resupply flights every few weeks. Those flights deliver food, replacement filters, spare circuit boards, medical supplies, and components for the life support hardware itself, because no mechanical system operates indefinitely. Every pump, every valve, every sensor is degrading. When something breaks on the ISS, the fix is straightforward. A replacement arrives on the next cargo vehicle. Remove that thread. That is what a Neptune mission requires. Every gram of food the crew will eat across a 15-year outbound journey must be loaded before launch. Every spare filter, every replacement circuit board, every surgical supply. There is no next cargo vehicle. There is no resupply flight. Whatever leaves Earth is all there is. Two options exist for food, and neither is clean. The first is to carry it. 15 years of food for a crew of fewer than 10 people runs to tens of thousands of kilograms. That mass compounds the fuel problem already discussed. The rocket equation does not forgive extra weight. Every kilogram of food requires more fuel to carry, which requires more fuel to carry that fuel. The supply chain buries itself. The second option is to grow it. Bioregenerative life support. Crops planted and harvested inside the spacecraft. Waste composted and cycled back into nutrients. A functioning agricultural ecosystem sustained inside a sealed metal tube for over a decade. The crew becomes farmers. They tend plants in a vessel moving through the outer solar system, managing soil chemistry and water cycles and nutrient ratios while simultaneously navigating, maintaining, and conducting science. Wait, a single crop failure could threaten crew survival with no resupply possible. Fungal contamination, a breakdown in the nutrient cycling, a failed grow lamp. Any one of these with no replacement system available removes a primary food source from people who cannot ask for another one. The hydroponic module is not a backup. It is the plan, and plans fail. Water carries the same logic, only more unforgiving. The 98% recycling efficiency the ISS achieved in 2023 is genuinely excellent for a station receiving regular resupply. But consider what 98% means across 15 years without any resupply at all. 2% of the water supply is lost with every cycle. That loss is small at first. Over months, over years, it drains reserves steadily towards zero. The systems maintaining that recycling efficiency must be kept running by the crew using only the tools and spare parts they carried at launch. A critical component fails, no spare exists. The water processing stops. Dehydration becomes fatal in days, not weeks, days. Oxygen follows the same chain. Electrolysis splits water into hydrogen and oxygen, giving the crew breathable air. Electrolysis requires electricity. Electricity requires the spacecraft's power system to function without interruption for the entire mission. On the ISS, solar panels supply that power reliably, but solar panels depend on sunlight, and sunlight follows the inverse square law. At 30 astronomical units from the Sun, where Neptune orbits, solar irradiance drops to 1/900th of what it is in Earth orbit. Solar panels at that distance produce almost nothing. They are not a degraded solution. They are no solution at all. The only viable power source for a crewed Neptune mission is nuclear. Either radioisotope, thermoelectric generators, which convert heat from radioactive decay directly into electricity, and which have powered Voyager 2 and the Curiosity rover for decades, or a compact nuclear fission reactor generating power through controlled nuclear chain reactions. Both exist in some form. Both have proven themselves on robotic missions. But scaling either technology to power crewed life support, active propulsion, continuous communications, scientific instruments, and all the systems a crew of living people requires for 15 years or more without maintenance from outside is an engineering problem that has not been solved. That phrase is worth holding. Solvable in principle, not the same as solved. Think about the difference between imagining a machine and building one that runs without failure for 15 years. The ISS has been continuously occupied since the year 2000. That is more than 2 decades of human presence in space. It is a genuine achievement, but that achievement rests on constant maintenance by the crew aboard, regular resupply every few weeks, and a permanent ground team of thousands of engineers monitoring every system around the clock. When the ISS develops a problem, the collective intelligence of an entire space program focuses on it within minutes. A Neptune spacecraft carries none of that infrastructure. It carries a crew of fewer than 10 people. Those people must simultaneously be scientists conducting the mission's research, engineers maintaining the spacecraft, physicians treating illness and injury with no evacuation possible, farmers managing the food supply, plumbers keeping water recycling operational, electricians diagnosing power system faults, and psychologists managing their own mental health across years of isolation. Consider what that demands of hardware. Engineers design components for operational lifespans measured in years. 5 years is common. A Neptune mission asks those same components to run for 15. Think of asking any appliance to run 3 times its rated lifespan, with no service, no replacement parts, and consequences for failure measured in human lives. The spacecraft is not a machine with redundancies waiting to absorb failures. It is a machine cannibalizing itself across the transit, exactly as described earlier, pulling parts from wherever they can still be found, keeping essential systems alive by compromising everything else. All of these problems are solvable in principle: closed-loop life support, bioregenerative agriculture, nuclear power for deep space, ultra-reliable long-duration systems. Researchers are working on each of them. Progress is real, but the engineering that exists on paper and the engineering that runs without critical failure for 15 years inside a sealed vessel, 30 astronomical units from Earth, are not the same thing. The ISS shows we can keep humans alive in space for years at a time. What it does not show is that we can do it without the resupply flights, the replacement parts, and the ground team of thousands that make every day aboard possible. Remove those, and the achievement the ISS represents transforms into something categorically different. Not harder in the way that a longer hike is harder than a shorter one. Harder in the way that a different problem is harder. A problem where the failure modes do not produce delays or setbacks. They produce deaths. And the life support systems are only one layer of what must hold. And if those systems fail beyond what the crew can fix, could anyone reach them? The answer is no. Probably not. Not yet. No. Every crewed mission in the history of human spaceflight has operated inside a framework of possible rescue. That framework is so deeply embedded in how we design missions that most people never consciously notice it. It is simply there, the way the floor is there. In 2021, a piece of debris threatened the International Space Station, and the crew sheltered inside their docked return capsules, ready to undock and come home within hours if necessary. The capsules are always there, always ready. The floor never disappears. Mars changes the framework, but does not eliminate it. During certain phases of an outbound Mars trajectory, a free return path exists. The spacecraft swings around Mars and arcs back toward Earth, trading time for safety. Months pass, sometimes close to a year, but the crew comes home. On the Martian surface, evacuation is harder, but pre-positioned ascent vehicles and Earth return spacecraft can be staged in advance. The floor gets thinner. It does not disappear. At Neptune, the floor does not exist. Once a crew commits to a Neptune trajectory and departs Earth orbit, there is no abort option, no free return, no pre-positioned rescue vehicle, no path back that physics allows in any time frame that matters. If a life support system fails in year 3 of a 15-year outbound transit, Earth cannot send help. Even if a rescue vehicle could be launched immediately, which it cannot because no such vehicle exists, it would take 12 to 20 years to arrive. The crew would have been dead for over a decade before anyone reached them. This is not a funding problem. It is not a political will problem. It is physics. No vehicle can cross the distance fast enough to help. The framework that has held up every crewed mission since Yuri Gagarin does not extend to Neptune. It simply ends. Shackleton's crew spent nearly 2 years stranded in Antarctica before he sailed 800 miles in an open lifeboat to reach a whaling station and organize their rescue. 800 miles of brutal open ocean. And at the end of it, there was a station, there were people, there was the possibility that someone could come. When Apollo 13's oxygen tank exploded halfway to the moon, Houston engineers worked through the night, improvising a solution in real time, and guided 3 men home on a damaged spacecraft using the lunar module as a lifeboat. Even Antarctic winter-over researchers, locked into months of polar darkness with no possibility of evacuation during the worst weather, know that when conditions clear, an aircraft can reach them. Every dangerous human endeavor in the recorded history of our species has included, somewhere, the scaffolding of potential rescue. Someone who might come. A cavalry that exists, even if it cannot always arrive in time. At Neptune, there is no cavalry. The phrase, Houston, we have a problem, carries inside it an entire architecture of assumption. That someone on the other end is listening, that they can help, that solutions can travel fast enough to matter. That architecture does not apply at Neptune. The crew is not operating with a thinner safety net. They are operating without one. Think about what that means in practice. Year 8, outbound. The spacecraft is roughly 20 astronomical units from Earth, deep in the outer solar system, past the orbit of Uranus, and still years from Neptune. The sun behind them has been shrinking for years, and is now a small bright disk in the rear view of the sky. The main water recycling pump fails. The backup failed 14 months ago. The crew repaired it then using parts cannibalized from the backup CO2 scrubber. There is no third option. The primary pump processes urine, humidity condensate, and wastewater into drinkable water. Without it, the crew has roughly 30 days of emergency water reserves for 6 people. They diagnose the problem, a bearing failure in the centrifugal separator. The bearing has been spinning continuously for 8 years. It was rated for 5. There is no replacement bearing aboard. The crew sends a detailed report. 4 hours later, Mission Control receives it. Engineers scramble. They consult the manufacturer, pull the original specifications, run models, and test repair approaches on identical hardware. 10 hours after the failure, Mission Control transmits 3 repair options, ranked by likelihood of success. 4 hours after that, 14 hours after the bearing failed, the crew receives the response. But the crew has already attempted their own repair. They had no choice. 30 days sounds like a margin, but a crew of 6 consumes water at a rate that makes every day precious. They could not afford to wait 8 hours for a response, let alone 14. They machined a replacement bearing in the onboard workshop and reinstalled it. The pump runs, but it vibrates. An imperfect fix. It might last 6 months. It might last 6 days. Mission Control's instructions describe a superior technique, a method that would have produced a cleaner bearing, a steadier pump, a repair likely to hold. But the crew's fix is already installed, and removing it risks damaging the housing. Now they must decide, live with the imperfect repair, or tear it out and attempt the better method at the cost of potentially making everything worse. They ask Mission Control. Another 8 hours pass before they receive an answer. Every equipment failure on a Neptune transit looks like this. Every repair is permanent because there are no second chances and no resupply. The margin between a functioning mission and a dying crew is the thickness of a bearing, the depth of a tolerance, the difference between a fix that holds for 6 months and one that holds for 6 days. But the truth was harder. The crew knows all of this before they leave. The point of no return on a Neptune trajectory arrives within months of departure, possibly sooner. Once the acceleration fuel is spent, the trajectory is set. The remaining propellant is allocated to course corrections and deceleration at Neptune. Nothing is held in reserve for turnaround. The crew passes the point of no return almost before the mission has truly begun, becoming passengers on a one-way arc governed by celestial mechanics that cannot be negotiated with. The fuel problem makes this irreversibility nearly absolute. Getting to Neptune requires acceleration, cruise, and deceleration. A return trip requires acceleration away from Neptune and deceleration back at Earth. The total change in velocity required for a round trip is staggering. Under chemical propulsion, the fuel mass needed dwarfs the payload by orders of magnitude. The spacecraft becomes essentially a fuel tank with a tiny habitat attached, and even that may not carry enough. Under advanced propulsion concepts, nuclear thermal, nuclear electric, theoretical fusion drives, the round-trip requirements remain formidable enough that mission designers quietly acknowledge the obvious. A crewed Neptune mission would most likely be one way, not as a dramatic choice, as a straightforward consequence of the rocket equation applied to the most distant planet in the solar system. The phrase, "never see Earth again," sounds like poetry. It sounds like the kind of thing someone says for effect, to give a speech a sense of weight. It is not poetry, it is a physics assessment, 12 to 20 years of one-way travel time, possibly unachievable return fuel requirements, radiation exposure accumulated across the transit likely exceeding any limit considered acceptable, life support systems required to run without failure for 30 to 40 years of round-trip duration, not poetic exaggeration, a straightforward reckoning with numbers that do not close. 60 years of crewed spaceflight have been built on a single foundational assumption: bring them back alive. Every mission, every vehicle, every abort system, every rescue protocol traces back to that commitment. A Neptune mission requires setting that assumption aside, not reluctantly, not as a failure of imagination or will or funding, as a consequence of where Neptune sits in the architecture of the solar system. The crew must understand this before they leave. They must accept it. They must consent to it, with full knowledge that the consent is permanent. Mars is hard the way bigger versions of existing problems are hard. More distance, more delay, more isolation, more risk, but problems that fit inside frameworks already under construction. Neptune is hard in a different way. The problems of duration, isolation, irreversibility, and human fragility at Neptune's scale do not have precedence. They do not have current solutions. They do not fit the frameworks that 60 years of crewed spaceflight have built. And that is only the beginning of what distinguishes Neptune from everything that came before. And then, after all of it, they arrive. Neptune resolves from a point of blue-black light into a world. A sphere of compressed gas and exotic ice, roughly 49,000 kilometers across. Its atmosphere is a mixture of hydrogen, helium, and methane, and it is the methane that does this to the color, absorbing the red wavelengths of the already diminished sunlight and scattering back a deep, cold blue. In the dim light at 30 astronomical units, the planet looks almost dark, not the vivid blue of Earth's oceans, something heavier, a blue that belongs to the outer solar system and nowhere else. The crew has spent years watching the sun shrink. Now they watch Neptune grow. What fills the view is not tranquil. The upper atmosphere churns with storm systems wider than continents, appearing and dissolving within years. Bands of methane ice clouds shear across the face of the planet, reforming into different configurations before the crew has time to fully map them. The same winds that made Neptune strange from a distance are stranger up close, not weather in any terrestrial sense. Something more like a permanent state of atmospheric violence sustained by a heat source no one fully understands. But the atmosphere is only the beginning. Below the cloud tops, temperature and pressure rise steadily with depth. The visible surface gives way to a mantle of superheated water, ammonia, and methane compressed into states that have no common name. And here is where Neptune becomes genuinely strange. Beneath enormous pressure, water is forced into a phase called superionic ice. The oxygen atoms lock into a rigid crystalline lattice, solid and fixed, but the hydrogen ions are freed from that lattice entirely, flowing through it like a current through a wire, simultaneously solid and liquid, not a metaphor. a real physical state, confirmed in laboratory experiments, existing right now inside this planet. Deeper still, the pressure climbs to millions of atmospheres. Temperatures reach thousands of degrees. Some models suggest that at these depths, the carbon stripped from methane molecules is compressed hard enough to crystallize, to become diamond. And those diamonds, denser than the surrounding material, fall. They precipitate downward through the planetary interior like hailstones, accumulating around the rocky core at the center. A core roughly the size of Earth, crushed under thousands of kilometers of gas and ice and exotic chemistry that no instrument has directly measured. The crew would spend weeks mapping Neptune's magnetic field. And here, Neptune resists explanation again. The field is steeply tilted relative to the planet's rotational axis, offset from the planet's geometric center, behaving in ways that do not fit the standard models used to describe how magnetic fields are generated inside planets. Why Neptune's field looks the way it does remains poorly understood. One more thing this planet does not explain about itself. But the crew has not come this far for Neptune alone. Triton hangs in the darkness ahead. The captured moon. The one that gives itself away immediately, if you know how to read it. Almost every moon in the solar system orbits in the same direction its planet rotates. Formation physics demands it. A moon that forms alongside its planet inherits that shared momentum. But Triton orbits backward, retrograde, moving in the opposite direction from Neptune's spin. That orbital direction is a forensic signature, written into Triton's path around the planet, that cannot be explained by formation, only by capture. Triton was not born here. It was seized. The leading hypothesis is that Triton was once part of a binary pair, two Kuiper Belt objects orbiting each other in the cold outer reaches of the solar system. When that pair drifted too close to Neptune's gravity, the planet's pull broke the partnership apart. One body was captured into orbit. The other was flung outward, sent tumbling away into the solar system's outer dark. The binary disruption that left Triton here also erased its companion. There is no way to know, at this distance, what became of it. What remains is a world encrusted in nitrogen and methane ice, its surface among the coldest in the solar system at negative 235 degrees Celsius. Cold enough that ordinary gases freeze solid at the surface. Cold enough that Triton should be geologically inert. Locked, silent, dead. The reading came back reversed. Voyager 2 photographed Triton's surface in 1989 during its flyby. What the images showed was not a frozen, featureless shell. The surface had been repeatedly resurfaced. Geological activity had been rewriting the landscape, and dark jets of material were erupting from beneath the frozen crust, nitrogen gas carrying dark streaks of material miles up into Triton's vanishing atmosphere, thin as a whisper, before falling back down to the surface in long, dark plumes. A moon at the edge of the solar system, at temperatures where nothing should move, erupting. Not dormant, not frozen, alive. The heat that keeps Triton active is thought to come from tidal forces. Neptune's gravity flexes Triton's interior as the moon traces its retrograde orbit, generating friction, generating heat. The same mechanism that keeps Europa churning beneath its ice shell. The same mechanism suspected at Enceladus. And because of that heat, some scientists now think Triton may harbor a subsurface ocean, liquid water maintained by tidal heating, hidden beneath kilometers of frozen nitrogen. An ocean world, captured from the Kuiper Belt, carried into the outer solar system by gravitational chance, potentially harboring liquid water in the dark. If a crew deployed instruments on Triton, conducted close flybys, landed near a geyser vent to sample what the plumes carry upward, they might find organic chemistry in that material. The kind of chemistry that elsewhere in the solar system has been interpreted as a signature of environments where life is at least conceivable. Triton looked, from a distance, like a scientific bonus, an interesting captured object at the edge of a distant planet's orbit. Up close, it belongs to a very short list of places in the solar system where one of the most significant discoveries in human history is genuinely possible. The crew would know this. They would hold that knowledge in the years it took to get here. And then, standing at what might be the most astrobiologically significant location humanity has ever reached, they would make their measurements, they would collect their samples, they would run their instruments and compile their data and speak their observations aloud into their recording systems. And they would wait, not for a response, not yet, just to learn whether what they sent home had arrived. 8 hours later, they would know that Earth had heard. Not the excitement, not the confirmation, not the shared moment of recognition that this matters, that this changes things, that the species has just learned something it did not know before. That would come, but it would come as a message traveling back across 4 light hours of space, carrying the reaction of a world the crew has not seen with their own eyes in more than a decade, arriving as text or as a face on a screen, slightly compressed, slightly delayed, belonging to a different present than the one the crew is living in. The discovery would be theirs. The moment of it would not be shared. And what that means for the humans standing on the surface of a moon at the edge of the solar system, having made the most isolated choice in the history of their species, is not yet fully contained in what we have said. The full weight of that silence is still ahead. All of it gathers here. The distance, the silence, the years of transit, the bodies that have changed, the world that has moved on, the discovery made in isolation. All of it converges into one quiet truth that the science alone could not have told you. The phrase is, never see Earth again. And it sounds like poetry. It sounds like the kind of thing someone says to be dramatic, to give weight to the moment. But it is not poetry. It is a precise description of what happens to a crew traveling to Neptune, operating on 3 separate levels, every one of them true. The first is optical. At Neptune's closest approach, Earth sits roughly 29 astronomical units away, deep inside the glare of a sun that has already shrunk to a piercing point of light. Earth is invisible to the naked eye. Through a telescope, it appears as a pale blue pixel, a single point of color adrift near the sun's position in the sky. Not a sphere, not a place you can recognize. A pixel, the home of 8 billion people, reduced to a speck you could mistake for a background star. The second level is communicative. The 4-hour one-way delay does not slow down conversation. It ends it. What remains are mismatched monologues. You speak, and 4 hours pass, and Earth receives what you said. Earth replies, and 4 hours pass, and you receive what Earth said. A single exchange consumes most of a waking day. Over months, over years. This is not delay. It is a different structure of existence. The shared present tense of human relationship, the thing that makes a conversation feel like contact, is simply gone. The third level is temporal. The transit takes between 12 and 20 years one way. Think about what 12 years contains. After 5 years, friends have made new friends who never knew the crew existed. The social fabric has woven itself around the absence. After 10 years, children the crew left behind have become adults who lived more than half their lives without a parent. After 15, the world has shifted politically, culturally, technologically. Language drifts in ways too subtle to measure, but too real to miss. A crew member who left Earth at 32 would return at 60 or 65 to a world that contains almost no one who remembers them as they were. And here is the thing that matters. Never see Earth again does not require that the crew cannot physically return. It only requires that distance and time make Earth, as a living reality, as a place where you belong, cease to exist for them long before they arrive at Neptune. The Earth they left is gone within the first few years of transit, consumed by time. What they carry with them is a memory of a world that no longer corresponds to the world that exists. That is not a small distinction. That is the difference between being away from home and having no home to return to. This is what the exile horizon describes. Not a line on a map, not a coordinate in space. The exile horizon is the distance beyond which a human crew is no longer functionally connected to Earth in any meaningful real-time sense. It is a gradient, not a wall, and it is instructive to walk the planets along it. Mars sits well inside the horizon. The communication delay is painful, running from a few minutes at closest approach to roughly 22 minutes one way at farthest. Travel time is months, not years. A Mars crew can still go back. Earth is still part of their operational reality, still part of their inner life, still a place they can genuinely call home because they will plausibly return to it on a timescale that their relationships can survive. Jupiter pushes closer, 35 to 50 minutes each way, travel time in years. Return becomes a major challenge, but Earth remains present in any practical sense. Mission control can still function, even with the lag. The crew is far, but not beyond reach. Saturn and Uranus push into the danger zone. At Uranus, the one-way delay runs past 2.5 hours each way. Travel time exceeds a decade. Abort options have nearly vanished. Life support systems are being asked to sustain human beings for durations no engineering has ever validated. The horizon is close. At Neptune, the tether snaps. Not stretches, not strains. Snaps. 4 hours of delay. 12 to 20 years of transit. Fuel for return that may not exist. Rescue infrastructure that cannot exist. Bodies carrying accumulated radiation damage and microgravity adaptation that cannot be undone. A world back home where loved ones have aged, changed, and in some cases died. An Earth held in memory that no longer corresponds to the Earth that exists. Neptune crosses the exile horizon. That is the astronomical irony at the center of this story. Neptune is inside the solar system. It orbits the same sun. By interstellar standards, it is practically next door, separated from Earth by roughly 4 light hours, compared to 4 light years to the nearest star. In the language of astronomy, Neptune is local. It is hours, and yet for a human crew, reaching Neptune would feel less like exploring the solar system and more like leaving it. The boundary that matters for humans is not the heliopause, not the sun's gravitational sphere of influence. It is much closer than either, and Neptune stands on the wrong side of it, but something else was happening. The crew would make discoveries at Neptune that dwarf almost anything accomplished anywhere else in the history of exploration. They would study a magnetic field tilted steeply away from the rotational axis, offset from the planet's geometric center, origin still poorly understood. They would track storm systems wider than continents, appearing and dissolving within years. They would deploy instruments near Triton, whose retrograde orbit tells the forensic story of a capture, a binary companion destroyed, a world flung outward into the dark, a moon left behind in an orbit that should not exist. They would sample the geyser plumes erupting from beneath the surface, sitting at minus 235 degrees Celsius, looking for organic chemistry, looking for the compounds that precede life. And if Triton harbors a subsurface ocean beneath its frozen crust, maintained by the tidal flexing of Neptune's gravity, a liquid water environment at the edge of the solar system, captured from the Kuiper Belt, then the crew standing at its surface would be present at one of the most significant astrobiological discoveries in history. They would wait 8 hours to learn that Earth had heard. Not heard and celebrated. Not heard and responded. Just heard. The celebration, the peer review, the public recognition, the cascade of scientific reappraisal that follows a discovery of that magnitude, all of it would unfold on a planet the crew cannot see, in a timeline they do not share, among people who have become, over 15 years of delayed correspondence, something closer to strangers than to colleagues. Discovery has always been a shared human experience. The moment of it, the "did you see that?" turned outward toward other humans who share the same present, has always been available. Even isolated explorers in the most remote places on Earth had that. They could turn to the person beside them. At Neptune, the crew can turn to each other. 4, 5, maybe 6 people, the whole of their human world compressed into one spacecraft, sharing the most extreme experience in the history of the species. And then they wait, and wait. This is the process by which Earth transforms from a home into a memory. Not a sudden break, a gradual fading. The crew knows Earth exists. They still care about the people on it, but Earth occupies a different category in their consciousness with each passing year. A historical fact, a place they used to live, a concept they carry inside them, fading at the edges like an image left in sunlight too long. The web of connection does not snap all at once. It frays strand by strand. First the optical anchor goes, Earth dissolving into a pale pixel they cannot find without a telescope. Then the communicative structure collapses, conversation becoming something that happens in geological time. Then the temporal displacement deepens until the crew and Earth are inhabitants of different presents, running parallel and unable to close the gap. Then the rescue framework ends, and they know no one is coming. Then the return option closes, and they know they are not going back. And finally, arrival at Neptune confirms what has been accumulating for over a decade. What remains is the silence, and the small company of one another. The profound implication of Neptune is not the planet. Neptune is extraordinary, yes. Its exotic interior chemistry, its baffling magnetic geometry, its captured moon with its geysers and its possible ocean, all of it is remarkable in ways that will occupy scientists for generations. But the deepest thing Neptune reveals has nothing to do with ice giants or superionic chemistry or diamond rain. It reveals something about the structure of the solar system we thought we knew. That exile begins inside our own home. The first genuine exile in human history would not occur when a spacecraft crosses into interstellar space. It would occur right here, inside the sun's gravitational embrace, at a planet on every classroom poster, every diagram, every model of our solar system ever built. The crew at Neptune would be the most isolated human beings who ever lived. Not because of equipment failure, not because of accident, because of physics, because of the fundamental architecture of the universe, which limits information to the speed of light and limits human logistics to the reach of chemistry and engineering that cannot stretch 30 astronomical units and hold. The isolation is not a problem to be solved with better technology or faster rockets. It is woven into the distance itself. Neptune is not the edge of the solar system. The Kuiper belt extends beyond. The Oort cloud beyond that. The sun's gravitational reach extends further still. But Neptune is the edge of human belonging. The last point inside our own star's domain where a person can still plausibly call Earth their home. One step further, and even that connection dissolves. The crew would look back through whatever telescope their spacecraft carries and find Earth, a pale blue pixel, barely distinguishable from background stars, 4 light hours away. A planet where billions of people are living their lives, unaware that a handful of their species is watching from the darkness at the edge of everything familiar, waiting for a reply that will take most of a waking day to arrive. Earth would still be there, still real, oceans blue, continents turning under clouds, but for the crew it would have crossed a threshold, from a place they live to a place they remember, from a home to an origin, from a presence to an absence that fills the sky with silence. That silence is the real weight of Neptune. Not the cold, not the wind, not the distance measured in light hours and years, and accumulated radiation. The silence is what remains when the web of connection, the shared present, the possibility of rescue, the visual anchor, the temporal overlap that lets a human being feel they belong to something larger than themselves. When all of that is severed, strand by strand, over the 15 years it takes to travel from one end of your own star's domain to the other, inside our own solar system, orbiting our own sun, there exists a planet so far away that reaching it would mean leaving behind everything that makes human life feel human. Not the biology travels with you. Not the intelligence. Your mind goes wherever you go. What you leave behind is the web. And at Neptune, the web is gone. What remains is the most profound solitude the universe has ever offered a conscious mind. A small warm vessel of life beside a blue-black world. The sun, a piercing point among indistinguishable stars. Home, 4 light hours, and a lifetime behind. They would be standing at the edge of us. And what lies beyond that edge, in the vast dark stretching outward from Neptune through the Kuiper belt, toward the Oort cloud and the threshold of interstellar space, is a question no human being has yet been positioned to ask in person.